Hi students, and today we'll be talking about cell potentials and voltaic cells. Now this is a redox reaction shown above where copper solid is reacting with silver ion to become copper ion and silver solid. And last time we learned how to balance this reaction, so if I write the two separate half reactions, don't need that actually, here I have an eraser. I am still learning how to do all this. And this forms copper aqueous. Oh my. And silver aqueous ion and form silver solid. If we were to balance these reactions electronically, we would have 2 electrons on the product side of the copper half reaction and 1 electron on the reactant side of the silver half reaction, and we would have to multiply the silver reaction by 2 so that the 2 reactions are balanced. Our resulting balanced reaction would be Cu. That is not a U, but it's close. All right, Cu solid plus 2Ag aqueous, and this forms Cu2 plus aqueous plus 2Ag solid. And in this reaction, we see that copper is giving electrons to silver, and silver is becoming silver solid, while copper is becoming aqueous copper. So 2 electrons are being transferred. And this is the basics for cell potentials and voltaic cells. This transfer of electrons can be utilized in a particular way so that we can generate electricity. And how we can do that is through a device called a voltaic cell. In a voltaic cell, we have the 2 half reactions split up into the 2 sides of this device. And on one side, if I can get my ink color here, oh, I keep doing highlighter. Why do I do that? Okay. On one side of the device, we have the half reaction with copper. So this is the copper side. And on the other side, we have the silver side. And we see here that copper is giving up electrons, and as a result, becoming copper 2 plus. Right? Just like in our half reaction, copper is giving up electrons, right? So copper is giving up electrons and becoming copper 2 plus. And on the other side, we see that silver is gaining electrons, and silver is also going from the ion form into the solid form. Just like in our half reaction, silver is going from the ion form into the solid form here. And so this is a device that utilizes the transfer of electrons because electrons can pass through a device like a voltmeter or a light bulb or a toaster or whatever you want to power. And we are able to use that electricity for work. Now, how do we know how much electricity is generated from this device? Well, what we can use is something called a cell potential chart. And the cell potential chart looks a little bit like this. Oh my. Yeah, let's keep these things. In the cell potential charts, we see that there are a bunch of half reactions shown and potentials in voltages if all ions are 1 molar. Remember, this is what this little circle means here, E representing cell potential. And we just have to find our half reactions. We see we found silver here. Silver is 0.8 volts. And we see, this is not it actually, because there's only transfer of 1 copper, but this is our copper half reaction. We have 0.34 volts. And so if we go back to our problem here, we can solve for the cell potential of this particular voltaic cell. And let me change the color of my pen here to something fun, maybe green. Remember, our cell potential for copper was 0.34 volts, but that was showing the reduction reaction. And this is the reaction of copper being oxidized. So actually our voltage for this half reaction is negative 0.34 volts. And remember, our silver reduction potential was 0.80 volts. And so if you wanted to find the total cell potential of our final reaction, all we have to do is sum these two numbers here. And this will give us a voltage of 0.46 volts. And so that means that this voltaic cell will generate 0.46 volts if this is run where copper is at 1 molar and silver is at 1 molar. Because remember, those were the standard cell potential, so everything is 1 molar. One thing to note is that as this reaction runs, more copper is going to be generated here. This is a terrible color to use, so maybe I will choose a different one. How about black? So more copper is going to be generated here, and more silver is going to be used here. And so this means this solution is going to get more positive as the cell runs. And this solution is going to get more negative as this cell runs. That is a G. And so in order for this cell to continue running and balance its charge, we need what we call a salt bridge. The salt bridge helps to balance out the charge as the cell runs. And we see here a salt bridge usually contains some ions that are positive and negative. And in this particular case, the negative ions are flowing towards the copper cell because it is trying to counterbalance the more positive charge that's being generated. While the potassium ions are moving towards the silver side of the cell because its positive charge wants to counterbalance the more negative charge that's being generated here.